In this video, we're going to learn about ionization of water and the concept of pH to measure the acidity or basic properties of solutions. Water has a tendency to ionize. What does that mean? That means at a very low frequency, when two water molecules come in contact, one of them steals a positively charged hydrogen ions from the other water molecule, giving rise to an entity which is called H3O plus or hydronium ion. And then the other molecule who has lost that hydrogen ion, so the hydrogen ion that has left leaves its electrons behind and forms a hydroxyl ion. And you notice that this reaction goes in two directions. That means this is a reversible event. Now, for this class, when we write this equation, we write it as this. Two water molecules, they ionize and they form a hydrogen ion. It's a positively charged hydrogen ion and a hydroxyl ion. So we're basically replacing this hydronium ion with this H3O plus symbol with this symbol of just the positively charged hydrogen ions. This is for simplicity. Just keep in mind that's actually this hydrogen ion is representing hydronium ions. But for the case of simplicity, we're just going to refer it to this symbol. As I mentioned, water dissociates into ions, and it happens at a very low frequency, but it does happen. Now, the amount of hydrogen ions in a solution is a very, very critical factor in how life functions. If we have too much of it or too little of it, the systems in our bodies don't function. So the concentration, the amount of hydrogen ions in bodily solution, in aqueous solution, is something that scientists keep a close eye on. And scientists have developed a scale which is called the pH scale, which goes from 0 to 14, to have a way of keeping track and measuring the concentration, the amount of hydrogen ions in solutions. So before I go on explaining the concept of pH, first we need to talk about the concept of concentration. Concentration refers to the amount of solute per unit volume of solution. Remember, we talked about solutions, and a solution is made up of solvent and solute. And when it comes to life, the solvent is water and solute is anything else that it's dissolved in water. And altogether, the water and those components that dissolve in water are collectively called a solution. So concentration refers to the amount of solute per unit volume of solution. What do I mean by per unit volume? That means for a given amount of volume, again, given quantity of the solution. Okay, so let's look at an example of a solution. This is a tea. I'm Persian and we drink a lot of tea, and we usually drink our tea with some sugar. So these are sugar cubes. We have the tea that eventually when we are going to drink is the solution, and then sugar is the solute. And here's the molecule of sugar, sucrose, that is the regular sugar that you're used to. So now, I don't like sweet drinks in general. So when I drink tea, I maybe use a 1/4 teaspoon, if at all, sugar in my tea. My son likes a little bit more sugar, so he puts maybe 1/2 teaspoon of tea. My husband really likes sugar, so he puts 1 teaspoon. So for a given amount of tea, we are each adding different amounts of sucrose into our tea. So the concentration of sucrose in each of these T's is different. On this end of the scale, we have a solution with a low concentration of sugar. Then this is the medium concentration. That's a high concentration. So now we have to talk about concentration and a concept called molarity. Concentration can be measured in all sorts of different ways, and I'm going to give you a few examples of them. So you can measure the mass of a solute per particular volume of solution. You can measure volume of solute per volume of solution, or you can count the number of solute molecules per volume of solution, which is what we did in the previous example. We have the number of sucrose molecules in the solution. So for this discussion, we're going to talk about this definition of concentration: number of solute molecules per volume of solution. This is called molarity. Molarity refers to the number of solute molecules per liter of solution. So it's a specific volume of solution. Okay? So molarity is a number of solute molecules per a given amount of solution, and that amount for molarity is a liter of solution. And how do scientists count number of molecules? How do they exactly do that? They're so little. Well, they do it one Avogadro at a time. This Avogadro was an Italian scientist who developed what's called the Avogadro number. So that was adopted as a way of counting molecules. So this is a huge number, and usually when we talk about it, maybe we talk about these 3 digits and then 10 to the power of 23. So that's a huge number. So this Avogadro number, this quantity, is called 1 mole. So if you have 6.02214076 times 10 to the power of 23 molecules, then you have 1 mole of a molecule. Now, how does that relate to molarity? Well, 1 molar concentration of a solute is this amount, this number of molecules of solute in a liter of solution. Okay, so that's called a molar concentration. Now, if you had a 5 molar concentration, you would multiply this number by 5. So, in order to have a kind of analogy to make this a little bit more relatable, imagine when you go buy eggs. So when we buy eggs, we don't just go buy 1 or 2. We buy a dozen eggs, because that's the standard of buying eggs, unless you go to Costco and buy a huge amount. But usually when we go to regular grocery store, we buy 12 eggs, and we have a specific name for that. That's called a dozen. So that's an analogy for a mole. A mole of molecules equals this many molecules, and a dozen eggs equals that many eggs. So I hope that helps you relate to this concept of mole better. So if you have 6.02, now I'm making it simpler, 6.02 times 10 to the power of 23 molecules of solute in 1 liter of solution, the concentration of solute is 1 molar. And why do I have these brackets here? Because when we refer to the concentration of a molecule, scientists put brackets around them, just to show, as a standard way of showing that, hey, I'm showing you the name of this molecule, I'm putting it in brackets, and I'm talking about, when I do this, I'm talking about the concentration of the molecule. Okay, so now let's go back. Now that we have an understanding of concentration and molar concentration, let's go back to water. So we said water dissociates, ionizes into hydrogen ions and hydroxyl ions. Now, if you have pure water, remember I said this doesn't happen very often in water. In pure water, the concentration of hydrogen ions and hydroxyl ions are both 10 to the power of minus 7 molar. So there's not that many of them compared to the rest of the water that you have. So in pure water, these concentrations are equal. Now, instead of keep referring to large numbers, and when we go and look at solutions that are very acidic, where you have a huge number of hydrogen ions, and then, or solutions that are really basic, when you have really huge numbers of this one or really low numbers of hydrogen ions, you have to keep giving these huge numbers that have a big decimal or a very small exponents. That's kind of cumbersome. So scientists decided to make keeping track of the hydrogen ion concentrations a little more manageable. That's why they developed the potential of hydrogen, which we call pH. So what is pH? pH is equal to, and a mathematical expression of it is minus log 10 of the concentration of hydrogen ions. And that is equal, so when you write this, if you put the concentration of hydrogen ions in pure water, we put that number in here. So the pH of water is equals minus log 10 of 10 to the power of minus 7. Well, you may say, well, that's really going from 10 to the power of minus 7 to this one. That makes it even more complicated and more difficult. Well, no, because then the pH actually becomes this exponent on 10 to the power of minus 7 and not including the sign. So we go from concentration of hydrogen ions in water being 10 to the power of minus 7 molar to saying the pH of water is 7. Okay, so that's how it's simplified. And that's how the pH scale has been put together. So you see water in the middle here. The pH of water is 7. Now let's talk about urine. Urine has a pH of 6 as shown in this scale. What does that translate into concentration of hydrogen ions? And this formula, remember the number that is the pH is going to be the exponent on the 10. So therefore, the concentration of hydrogen ions is going to be 10 to the power of minus 6. Now, this means that concentration of hydrogen ions in urine is higher than the concentration of hydrogen ions in water. Why? Because 10 to the power of minus 6 is 10 times larger than 10 to the power of minus 7. So you may have noticed that as the concentration of hydrogen ions increases, the value of pH decreases. Another important thing to take notice of is that even though in pH we go by units of 1, so we go from pH of 7 to pH of 6, when we translate that into concentration of hydrogen ions, that actually translates into a 10-fold difference in concentration. So when I go from 6 to 5, it's 10-fold difference. When I go to 7 to 5, it's 100-fold difference. Remember that. Now try the same thing for seawater and come to your discussion and check your. So what are acids and bases? Acids and bases change the pH of the solution. And how do they do that? Well, an acid is a compound that donates hydrogen ions to solution. You may have heard of acids like hydrochloric acid, sulfuric acid. And a base is a compound that does the opposite. It reduces the concentration of hydrogen ions in a solution. So it either reduces the hydrogen ion concentration, either removes the positively charged hydrogen ions, or it donates hydroxyl ions. And we use acids and bases in order to form all sorts of different solutions of pH that at a pH that we want. Now, having a stable pH in life solutions is very, very important. If for example, pH of our blood changes slightly, then we get really in trouble, and it may even cause death. So luckily, we have buffers in our bodies that keep the pH of our solutions to change. And we also use buffers when we prepare solutions in laboratory to keep the pH constant so it doesn't change, let's say, during a chemical reaction. So how buffers work? Buffers accept hydrogen ions when it is in excess in the solution, and they donate hydrogen ions when it is depleted. So buffers usually exist in a solution as in two different forms: the molecule that is separate from its hydrogen ions, and a form of a molecule that is bound to the hydrogen ions. So when the hydrogen ion concentration goes up, this reaction moves towards the right, and when the concentration of hydrogen ions go down, this reaction moves to the left. Now, a very important buffer system that exists in your body, in your blood, is the carbonate system that helps keep the pH of your body at relatively constant. So the CO2 that we exhale, it dissolves into water and then forms what's called carbonic acid, and the carbonic acid dissociates into carbonate and this hydrogen ion. So this buffering system allows our pH, the pH of our blood, not to change considerably. So, for example, when we hyperventilate, we basically are breathing too fast, and maybe the amount of CO2 in our blood increases, and then our blood becomes a little bit acidic, and we get all sorts of symptoms. So when we breathe that fast, this system in our blood can't really catch up. So keeping a relatively constant pH in our body is very, very important, and thankful to the buffering systems in our body, we can survive most pH changes. Now, speaking of excessive carbon dioxide, the excessive carbon dioxide that we're putting into the atmosphere by burning fossil fuels is some of them goes into the atmosphere, and a lot of them are absorbed by the ocean. So water not only moderates temperature by absorbing extra heat, it also is absorbing extra CO2. So when CO2 is absorbed into water, it interacts with water and forms the carbonic acid. And then the carbonic acid in the ocean dissociates and creates carbonate. Now, many sea creatures have an exoskeleton, and they use carbonate that is in the ocean to form their shell. When we have excess CO2, this carbonic acid, extra carbonic acid, is going to release an excess of positively charged hydrogen ions, which is going to compete with these creatures for interaction with these carbonate molecules. So the hydrogen ions are going to move it away from these sea creatures, and if we don't have these carbonates available to them, they start dissociating. So that's another negative effect of global warming. And another thing is that it also reduces the pH of the oceans, which is again not good. So work through this problem and answer it, and come to discussion to check your words, and actually this one as well.